So I'm Ravi, I work in the Google office in Mountain View, and I'm going to talk something about discrete choice. It's different from the talks that you have been hearing for the last 3 days. It's a slightly different topic, but there will be some notion of graphs, and I hope you can connect your work to this somehow. Okay. And this is joint work with Flavio, who is in Sapienza in Italy, and Andrew Tompkins, who's at Google. Okay. So what is discrete choice? This is a field that's been around for the last many decades. It's typically not well studied in computer science or even discrete math settings, but it's a field that has had a very rich history with many Nobel prizes and so on. And it's mostly studied in economics and social sciences. And I'll give you a brief glimpse into the field by giving a short introduction. So what's the problem here? So you have, imagine a random user, and your goal is to go to a restaurant. So you're presented like 3 choices, and if a random user might pick to go to the pizza place, that's somebody can do that. And if you pick another person, he or she might want to go to a hot dog place. And this is a very common setting. You know, if you came on the trip yesterday, there was a choice problem, right? So we were deciding whether to stop at the metro for the toilet or whether you want to go to the the restaurant there for the toilet. So this is a very common setting, you know, every one of us faces in day-to-day life. Okay. So you have a random user, think of a random user, and you have a set of choices, and you want to impose a distribution on the choices that you have. Right? In this case, there are 3 items, and you want to pick one from this set. And you want to know what is the distribution a typical random user would do. So in this case, it could be like, you know, 10/5 most people who want to go to the pizza place. Okay. And for historical reasons, we'll call this subset as a slate. So because you're often given a slate of choice and you want to make a selection from that slate. But the same user could be given fewer choices. For example, you know, for some reason the middle restaurant is closed or something else happened to it. And the same random user given a different slate may have a slightly different way of choosing from this choice. So in this case, it could be like 70 versus 30. Right? And the goal of discrete choice is to, how do you learn these probability distributions that govern the choice in a very generic slate? Now you're somebody and you're given a subset, and you know that there is some underlying distribution of how people choose from the subset, and your goal is to learn the distributions. How do people make choices? And here is a more compelling example. This is Google search in Rome, and I want to go and eat at a place. So I choose restaurants, and I'm given a bunch of results here. And I'm a random user, and I pick. This is a probability with which Google knows that I'm going to pick. So it's in Google's best interest to show the answers in this sorted order, because they want to maximize the probability of picking the top result, or in which case they want to show results such that I'll be happy with the top ones, right? That's a general goal. So here I might pick this one with probability 45%, 0.45. But maybe I'm going to the restaurant very late. So in this case, I'm going after say 1 a.m., in which case this restaurant will be closed. And Google knows about it, and so it gives me a subset of the restaurants I saw before, right? And suddenly my probability might change, because I might say, okay, this is too late at night, I don't want to go to the 4th one, I might go to the 3rd one more often. So in this case, the probability actually, all the mass in the last restaurant, the 10% mass went to this 3rd restaurant here. So it became 30% now. But Google doesn't know about it. So therefore it still gives me the previous old ordering, in which case the correct thing would have been to swap these 2. Right? So in general, quickly learning the winning distribution, or the distribution, the choice that actually the user is going to make on a given slate, is very important from application's point of view, because that's going to make the user happy. But if you think about it, it's not going to be easy, because any subset, there are going to be exponentially many slates. You know, for under various circumstances, the slates that are given to the user are going to be very different. So how do we actually even learn this thing in an efficient way? And that's the whole theory of discrete choice. How do you model this and how do you show results in this? Okay. So in this setting there is usually a universe, a finite universe of say 1 through n, and as I said, slates typically denote non-empty subsets of this universe. And the model, how do you model this? You model that by a function which takes a slate, a subset, and gives you a distribution over the slate. So given a subset, it tells you with what probability each item in the subset will get chosen. And historically discrete choice models are used to codify rational behavior. Now you want to assume that people are rational, and so you want to model this making that assumption. So in this example I have indicated f to be a very general function, but in practice this is not true. What happens is that if given two slates s and t that are highly overlapping, it's more likely that the functions f of s and f of t will be somewhat related, right? So this very general setting doesn't capture that, but that's something that that's good to keep in mind. So keeping that in mind, there was a nice work of Marshak in 1960s, motivated by like a lot of work before, who introduced what is called a random utility model. So in this random utility model, there is a distribution on user utilities. Think of utilities as I am a user, I have a utility for every object in the universe. And there is a distribution on users like me. So distributions are basically values from the universe to some real numbers. Okay? And each user is chosen from this distribution, IID, and given a subset, the user is going to pick the maximum useful thing in that subset. So that's a very, very natural thing. So I given a subset and then I apply my utility function to the elements in the subset and I pick the one that has the maximum utility. Okay. So this naturally captures the constraint that I was mentioning. For example, if you take any subset T and take its super subset T union some element I, then by the fact that the distribution is fixed and you pick IID from that distribution, the probability that you pick some element J is at least as the probability that you pick from T union that element I. So in other words, if two sets S and T overlap significantly, then the probabilities of picking elements from the subset are somewhat related. So that's actually good. And this also as you think, if you imagine utilities for every object, this actually can be thought of as a rational decision user would make, right? I mean you don't know anything about the utilities, but everybody would go for the best choice given a slate. So that actually is a good is a reasonable thing to assume. Okay. And since if you notice, all you really care about is given a slate what gets picked, the actual utility values don't matter. So therefore you can assume that instead of this being a distribution on functions from universe to real numbers, you can assume that it's a distribution on permutations. So because any ordering, so all you care about is the ordering, the order of the utilities is the one that matters, and so I assume that there is a distribution on the permutations and you pick the top element in the permutation. That's a simplification.
This example,
yeah.
This inequality is just an example.
Example, yeah.
Supposed to bring this
Oh no, this is true actually in this case because the D is like IID, right? So it's basically yeah, that's why I mean it's IID from the same distribution. So D is fixed. It can be arbitrary, but it's IID. So you will get the fact that now you'll see this element more. So yeah. Okay, here is a more concrete example. So you have two users, the yellow and the red, and you have three choices. Now the yellow user prefers the yellow bus over a green train over a red car, and the red user prefers a red car over a green train and a yellow bus. Okay, these are two users. And suppose the distribution of the users, like there are 60% yellow users and 40% red users. Right? And pick a random user, and you're given a choice, like I want to choose between train or a bus. What should I do? So if first of all, given this choice of slate, the car option disappears because it's no longer relevant, and the question is what will the user do? Of course, if the user is a yellow user, we know that the yellow users like the yellow bus, so they will pick the bus, right? On the other hand, if the user is a red user, then we know that the red users prefer this thing, and therefore the red user is going to pick the train. Yeah.
Earlier we were just taking users. Right now, yellow user, orange user, what is the difference in users?
So think of each user as a distribution over utilities, which I argued that you can assume it's a distribution over permutations. So the yellow user likes this permutation, and the red user is from this permutation. So since they are 60% yellow and 40% red, effectively for this slate, for a random user, 40% of the people will pick the train and 60% will pick the bus for the slate. And in fact, if you enlarge the slate to include the green train, because the train is never the top choice for anybody, it will get picked with 0 probability. So the question is, how do you learn this probabilities for any given slate? That's the whole question behind this discrete choice. Is the setup clear? Okay. So you're given a universe n, and you're given an unknown distribution on the permutations on the elements of the universe. And now given any slate, any subset, let ds of I for I in the subset be the probability that a random permutation, that's the random permutation according to this distribution, picks I, makes I the top choice in the subset. Okay. So that's a formulation of the random utility model. Alright, so just set things straight, here's a concrete example. So in this case, the subset could have distributions for apple at 20%, an orange 5%, and grape 75%, and therefore the probability that the grape would be the top choice for this subset is 3/4. Alright, and the goal of learning here is I want to learn the choice, the distribution of the choice for every subset in the universe. So that's a setup. Okay, so the first observation that we want to make is that the actual learning problem will depend on what kind of access I have to the oracle. Remember, like here it's like an oracle model, right? Somebody gives me the distribution, so I have an access to the distribution. I could maybe query and get some samples from the distribution, or I could give a slate and get the topmost element from that. So it will turn out that the complexity of the problem will depend on what exactly you allow the algorithm to access from the oracle. So first simple observation is that even though the number of the distribution is arbitrary and it's over some unknown support, there is always what we can call a core set of a small number of random independent permutations that can be used to approximate arbitrary distributions. So that's actually a interesting fact. You can show that using some simple tail bounds, but there is a very polynomial many, in fact like quadratically many random permutations that can approximate the winning distribution on every slate really well.
Here you mean obtaining the entire permutation, not just the top one.
Yeah, the distribution actually can obtain the entire distribution for every slate, right? So, and that can be done by, the algorithm is very simple. I assume the distribution is accessible, so I just sample the distribution independently and I take like this many samples and I just answer accordingly. That's it. And you can show using Chernow bounds that this actually will work, will approximate the winning probability for every set of samples, for every random slate, for every slate with high probability. Okay. So this turns out to be something called mixture of multinomial logics, which I'll come to that later. Now why is this observation interesting is because it's actually a useful observation to have. Okay. So the question now we ask is this reasonable? Now we have been assuming that we know for a random user that this user is going to either know the distribution of how he or she is going to pick from the slate, or in other words the order in which they are going to use. Is that a reasonable assumption to make? The answer is no, because it never happens in practice that I tell like Google, I'm going to choose this one with, this is my first choice, this is my second choice, this is my third and fourth. You may never do that, right? So it's not a feasible assumption. Instead we actually observe only the click. So Google knows that this is the top choice the user made, and therefore that's the winner of this permutation in this subset. That's the only information that we give it to the system, right? So assuming that I know the entire distribution over the slate is not a reasonable thing. Instead, what I can only assume is that given any slate, there is an underlying permutation, and all I get to see is the top element of the permutation, because that's the one that user indicates to the system. So that's a choice, that a practical choice that you have to make. Okay. But
If they're two terrible restaurants that nobody ever picks, you can't compare them with this data.
You're right. So that nobody picks a restaurant, yeah, it's too bad. But the model,
Even though one is better than the other, you never see it.
you never see it, yeah. So here the model assumes that for every slate the user will make a choice. So I mean you are kind of forced to go to the bad one. So yeah. Okay. So, and it's much easier to ask, even if you want to conduct a survey like what Reinhard was telling yesterday, like questionnaires, it's much easier to ask a preferred option from a slate rather than tell me, okay, what's the probability that you like this one, this one, this one, so on. So it's much easier. So it's a much more reasonable model to keep in mind. Okay. So what is the algorithmic problem here? So we want to study the RUM learning, we call that RUM, the random utility model, from an Oracle perspective suggested by the application actually. Okay. And the only thing that you can do is that the system can propose slates to the users. Now Google can show a bunch of restaurants or a bunch of movies, and it gets a feedback from the user saying this is my top choice. So that's a reasonable assumption. And the algorithm actually can query the slates in an adaptive or non adaptive manner. That doesn't matter, because you can always do experiments, right? You can say that, okay, I want to know what is the user behavior on this subset, so therefore I'll show the subset of the user and see how they react. So that people do that all the time, right? So like an experimental test. Okay, and it can for every slate you can assume that you know the winning distribution, actually, because given any slate I can query that many times, so that over many random users I can approximate, okay, 75% of users want this as a top choice and 25% and so on. So I can assume that even though I only get the winner, by doing this independently many times, I can get the winning distributions approximately for any slate. That's actually a reasonable assumption. Okay, and there are two kinds of oracles, just to formalize what we are going after. We have two kinds of oracles that are interesting. One is called the max sample oracle, which is the more natural one, which is you're given a slate, this oracle picks a random user, which is like equivalent to picking a random permutation pi, and then returns the element in the slate that is ranked highest according to pi. This is a very, very natural, most reasonable distribution. A slightly stronger assumption is what we call max dist, which given a slate, this oracle returns the entire distribution, the winning distribution. As I argued before, this is easy to approximate if I have enough of this. You can always approximate the winning distribution, and therefore for just pure stylistic reasons, we'll assume that we know this distribution exactly. Now that's okay. That's a reasonable assumption. So I know this given any slate, this oracle will return the winning distribution for this slate exactly over the queries. So that's okay. These are the two assumptions oracles will work with. Here's an example. So we have the slate, and max sample of this slate could pick this as the permutation in its mind and return that, okay, orange is the most preferred item, but max dist would return the actual probabilities of each of these items being the winner. So that's the setup. Okay. So first we'll start with the bad news, that this problem in this most general form is actually hopeless from an algorithmic point of view. So even with the more powerful max dist oracle, remember max dist gives you the exact distribution over a subset. To learn the distribution for every slate, remember our goal is, like, given any slate I need to know what is the distribution, right? That goal is impossible to achieve with polynomial many queries. In particular, you need exponentially many queries to be able to learn this slate exactly. So in other words, what we show is that with little of sub-exponential number of queries, there will be some set where the expected total variation is going to be large. Okay. And in fact you can trade off between the number of queries here and the error you get. So this is just as an example. And the construction actually is quite simple. What we do is we construct a distribution and permutation such that you're given any arbitrary set S. For all the slates that are not S, the induced distribution is uniform, but the distribution on this slate is not uniform. Therefore any algorithm that has to approximate the slates will have to unfortunately look for the special slate, and therefore it needs to have exponentially many queries, right? So any algorithm will have to use 2 to the n sets to discover the special one, because every other thing is uniform, so you know that, but there's some hidden thing there which you need to find, which is kind of far from uniform. And that is by a simple construction, so basically suppose you're given this special set S, you choose some element say kappa in S, and you define a permutations such that the set of bottom S elements of pi is not the given set, then you make it to be uniform 1 over n factorial, otherwise you set the probability of this permutation to be something special. So it's just a simple construction that considers the actual set that you are given, and that you design a distribution that works according to this set. And by choosing this constants carefully and so on, you can set up the desired result that you want. So the details are not very important, but the more important thing is that very naively if you try to solve this problem, then you are faced with the lower bound issues. So you need very large number of queries to be able to even reasonably solve this problem. Okay, so what's the hope? I mean, it looks like we are stuck at step 1, right? We are not able to make any progress. We need exponentially many queries to be able to approximate the distribution. So what is a positive result that we can hope for? The important thing to keep in mind is that even though the model says the distribution on permutation is arbitrary, in reality it's not, right? There are so many users here. This user could like this ordering, it likes elements A greater than B greater than C greater than D, but another user could have a slightly different ordering, but the number of different orderings that actually exist in reality could be bounded. Number of different kinds of users could be bounded, because maybe I like Indian food and I'll place all Indian restaurants above non-Indian restaurants, but if you pick somebody else they might like some other cuisine, and so they would have their own ordering. So it's reasonable to assume that the support of the distribution of the underlying distribution is actually small. That's a reasonable assumption that we see in practice. Even though people have individually have different tastes, but probably they can be clustered into like classes which have very identical tastes or very largely similar taste. Okay. So the assumption that we make is there are only a few types of users. So how do we work with that assumption? Okay. So now the loading problem can become more tractable, right? So if there are only k types of users, then what we can show is that you can reconstruct exactly all the slate winning probabilities that you want with order nk calls to the max dist oracle. That's the very powerful oracle. And if you relax that oracle to the weaker one, max sample oracle, which is more reasonable, then you only lose the polynomial factors. So you can get a similar reconstruction algorithm to approximate the winning distribution to within any given error. So basically the whole problem becomes tractable once you assume that the support of the underlying distribution is bounded. Okay. And how does, I'll just give you a glimpse of how that proof works. As a main tool is like a oracle transformation tool. So what we do is that we'll obtain a new oracle that in a sense is equivalent in expressive power to the both max dist and max sample oracle, but still makes what we can learn about the unknown distribution very explicit. So I'll go into the details a little bit more. Okay, that's the main idea. And what is the intuition behind the idea is the following. So you have this, suppose this is the distribution on the underlying 4 different orderings. Remember instead of 16 permutations I only have 4, so already I have made an assumption here. And now this distribution induces a winning probability for every slate. So imagine the slate AB, by look at this, only this user likes A or B and they occur 30% of time. So d of A for the slate AB is exactly 3 over 10. And if you look at the slate AC, then you see that this user likes A over C, this user likes A over C, and this user likes A over C. So only this one doesn't like. So the probability of A winning given a slate AC is 9 over 10. So in this way you can write so probability of winning probability of C winning over the full slate is 0. So this distribution gives rise to this winning probabilities. But we know that this is we're not going to see this, right? Because users never give the order in which they prefer stuff. You only observe this. You're given a slate. I see that 30% of users like the value A in the slate AB, and so on. Okay. So this intuition of going from the winning distributions to actual winners gives rise to this tool, what we call the head distributions. So the idea is very simple. So you're given a set, say H of elements, and let some element S need not belong to doesn't belong to H. So let PHS be the probability that a random permutation has the elements of H in any order as a prefix, followed by S at position H plus 1. Okay. So here's an example. The subset H is 4, 6, and the element S is 2. So probability of this 4, 6, 2 is exactly that you pick pi from this unknown distribution, and pi begins either like 4 more than 6 more than 2 followed by whatever, or 6 more than 4 more than 2 followed by whatever. So basically it puts H in the beginning in some arbitrary order, we don't really care, but S occurs in the H plus first position. So this is a really crucial tool to be able to do the transformation that I talked about. Okay. So why are these useful? So the claim is that if you understand head distributions, then I can construct this should be a subscript, the slate winning distribution for any slate. Why is that? So what is ds of S? It's a probability that this element little s wins in this slate S under this permutation pi, chosen according to the unknown pi, which is exactly means that pi begins with a set of elements not in S followed by S, right? Which means that pi is of the form x1 through xi, where x1 through xi doesn't intersect with S, followed exactly by S. S is the first guy from S to occur in pi, which is exactly the sum over all subsets of T from the universe n minus S, Pt of S, which is the head distribution that we define. So head distributions are a very natural way to go to computing the winning probability for any slate. Okay. But head distributions turn out to be algorithmically more easy to manipulate. Okay. Why is that? And this is the way you learn head distribution. The claim is that head distributions you can learn using max-dis oracles, and that's a very simple inductive observation. For example, if I query the oracle with the entire slate 1 through n, I get the following. I get, remember it's a max-dis oracle, so it gives me the winning probability for every element in the universe. So dn of I is exactly what it is. It's a probability that pi begins with I, right? So I is a winner in the entire slate, which is exactly by definition P of empty set comma I. And inductively you can show that it's actually, you can observe that P of big S comma little s is exactly the winning probability of the slate without of this quantity minus the inductive quantity operating on smaller subsets of the head distributions. So therefore by learning the head distributions I can actually slowly inductively build this quantity P of S comma S. So that's actually great news because you can do this very well. But what about the efficiency? This still says that there are many times you need to query the oracle, but that's where the assumption about the support comes. You can show that if there are only k permutations in the support, then there are at most k pairs of head distributions which are non-zero. That's the key point. So therefore I can, making this assumption, I can learn these things efficiently in terms of support size. So basically head distributions give you a way to go from arbitrary exponentially many slates to some quantity that's non-zero only for support size. That's a way to think about it. Okay. So as I said earlier, we can learn all the head distributions using nk max dist queries, and if you want to go to the max sample, the more realistic practical queries, then you lose slightly more factors, but they are still reasonable. Okay. So this is a positive result, right, because we started with the negative result saying that if you want to approximate slate distributions, that's going to be hopeless with a sub exponential number of queries, but if you make a more practical, slightly reasonable assumption of bounded support, then you can do things more efficiently. Okay. So that's actually basically the difficulty in dealing with the whole area, that if you don't make the right assumptions, then the problems become highly intractable. Yeah. So the one assumption that we made was a system of few users, right? There are only few types of users, and I can show a positive algorithmic result in that regime. So I'll briefly touch upon two more positive results in these things. The first is what we call multinomial logits. I'll describe what it means, and the next is MNLs on graphs. Okay. So multinomial logit was introduced. It's a very famous paper of Bradley and Terry from 50s. It's a very special case of RUMs actually, and here is the model. You're given a universe of items, and every element, every item in the universe has a positive weight, say a sub u. Okay? And for a subset, for a slate of u, the probability of choosing u in the slate is actually proportional to its weight. So therefore, you're given a slate S, the probability of choosing u is exactly a sub u divided by the a sub v for every v in the S. Okay. So, and notice that this is a key factor, this is a normalizing factor, because you're given a subset, you restrict your attention to the subset. It's like a conditional probability, right? It's attention to the subset, and then you choose from the subset. Okay. This is the MNL model, and here's an example. So we have the 6 items, and this the weights could be the numbers are the weights, and you want to construct a distribution permutation of this weight. So I pick the first element, say the sum of this weights is 17, so I pick the first the red one with probability 3 over 17. The remaining sum is 7, 9, 14. So I pick say 5 with probability 5 the yellow one with probability 5 over 14, and so on. So the MNL, which is basically a weight for every element, naturally gives rise to a distribution on permutations, because I can generate permutations according to this weight system, right? So by picking the next item on the permutation at random from the remaining ones according to the probability proportional to the weight. So it's a very natural thing. So therefore MNLs imply RUMs. Okay. And the goal in this MNL is actually much easier. No, you're not trying to learn the winning distribution for every slate, but the problem is actually simpler. All we need to do is learn the weight for every item. That will completely define the model, right? So for so what do we get? We assume that for any slate, like the max dist oracle, we assume that for any slate we get the choice distribution, say the max dist oracle gives you the exact distributions, right? So I have an MNL, how do I learn the weight? This turns out to be an easy problem, because for what I do is that I take elements 1 through n minus 1, query the MNL with using the slate I comma n for I in 1 through n minus 1, it will give me this distribution ai divided by ai plus an, and of course 1 minus that. I can do this for every element, and what do I get? I get a linear system. So ai a1 over so I get this linear system, and since some of the ai's can be assumed to be 1 because it's all normalized, I can solve this linear system and I can learn all the weights. It's a very easy problem, right? So I can learn MNLs in a very trivial way by just querying this. Okay. So MNLs can be learnt with a linear number of queries and using slates of size 2, because I just need to ask, like, between these two items which one do you prefer, that's it. Or actually the probability that you prefer one over the other. Okay. But how good are 1MNLs? So I claim that 1MNLs are not very useful, and this is actually well known. It's not here's an example. There are two kinds of users, and there are two kinds of restaurants. There's a vegan one, and there is a burger place. Okay. And the vegan user, who's appropriately colored green, chooses the vegan restaurant mostly, and the non-vegan user chooses the burger place. And this is, so they really like the vegan one really likes the vegan place, and this is the place. This is all fine. This is like 2MNL. 2MNL can capture this. But suppose so assume that there are like half of each type of user. Okay. So in effectively vegan places get picked half the time and non-vegan places get picked half the time. But suppose there's a third restaurant opening, a new vegan place opens, and this is the choice. So this vegan person prefers this vegan place 4 times more than the other one, but the non-vegan person doesn't really care. They always want to go to the burger. And so the effective slate distribution becomes something like this for the entire slate. If you give me all these 3 restaurants, they get picked with probability 40%, 50% and 10%. But if you try to express this, the intuition that the choice, vegans always go to vegan place and non-vegans go to the burger place, then the constraints you get from trying to express that using 2MNL is not possible. You can show that an MNL cannot express the constraint because of the fact that I try to incorporate all these constraints about different subsets which have different semantics into this single system. Okay. So the bottom line is that 1MNLs are not sufficient to capture very common settings, and the reason is we try to model the entire population as a single type of user, which is a basic problem. In fact, what we really have is 2 types of users. We have vegan users and non-vegan users, and they behave in different ways, and that leads to, in other words, when you introduce a new item like a new vegan restaurant, it should cannibalize, in a sense it should pull users away only from vegan types of users, because non-vegan users don't really care whether you open another one or not, and any such new vegan restaurant should only affect vegans, and this constraint is not expressible with 1MNL. And this has led to all this choice theorists to look for other kinds of models, and a particular model is a MNL mixture, and that naturally captures the 2 types of population that we are dealing with here. And here is an example of a 2MNL mixture. For every universe there are 2 weights for every items, A sub u and B sub u, and for a given slate S, the probability of choosing a u and S is equal to a linear combination of these 2 choices. So there is a mixing weight gamma, and the first user could be like a vegan user, chooses this restaurant, this slate with this choice probability, and a non-vegan user chooses according to his own probability. And we'll consider only uniform mixtures. We'll assume that now these are half-half. So this one is able to capture these 2 types of users. Okay. So why is it useful? So MNLs are very weak, but MNL mixtures can approximate any RUM arbitrarily well. This is, so McFadden got a Nobel Prize for proving results along this form. So they are very powerful actually. MNL mixtures are very powerful. In fact, we show that you only need a polynomial. The course set result I showed you earlier, that n squared over polynomial epsilon squared, that says that you don't even need that many mixtures. You only need polynomially many mixtures to approximate any RUM. So this is how the situation looks. You have choice models, RUMs are sitting inside that, and you have MNLs sitting way inside that, but they are weak. But this thing I tried to draw, it's an approximation that claims that they can approximate any RUM arbitrarily well. Okay, they're quite powerful, and therefore the learning problem becomes very important. How do you learn 2 MNLs? You have 2 weights for every item. How do you learn that? Okay, and again we'll assume that we get the max dist oracle. We have the distribution exactly. So how about I try the same 1MNL idea? Now I query slates of size 2 and I get this as an answer. Assume it's 2 uniform MNL, so it's like half-half probability. Can I use this to learn? It turns out it's not enough. So 2 slates are probably not enough to learn 2 MNLs, and there's a simple counterexample for that. Okay, I wouldn't go into the details of this, but that's a counterexample. What about 3 slates? Okay, I query the MNL using slates ij, ijk. I get the distribution. So basically this is the distribution for ij, this is the distribution for ijk. So probability of winning I is like ai divided by ai plus aj plus ak plus bi divided by bj plus bj plus k. So I get a polynomial system here. So can I solve this? So even though it is finite, they are talking about few number of variables, it turns out that solving this actually is non-trivial. Now we tried using Mathematica or Maple kind of tools to do that. They can't do it over like 2 or 3 days actually. So but you can analytically show that this system of polynomial equations actually has a unique solution, and it's a fairly messy proof. Yeah. So what it means is that using the winning probability for 2 or 3 slates is enough, uniquely identifies the 2 MNL mixture. Okay. And by querying the MNL on slates of size 2 and 3 of different slates, I can patch them together to obtain the final result. Actually, I can learn or I can identify the mixture by doing this small number of queries and patching them together. In the interest of time, I'll skip this. Okay, this is the main result. So that says that there is an algorithm to that performs max-list queries on slates of size 2 and 3 that reconstructs a weight for any 2 MNL, okay, for uniform 2 MNL. That's the result that we know. Okay. So I just want to give you a very brief into graphs, because there's conferences on graphs. I don't want to miss this part. So the problem we consider here is motivated by the MNL problems. So here is the problem. You are given a graph and every node has a score. First of all, you can define a Markov chain based on the setup the following way, using motivated by MNL choice. The Markov chain's transition is MUV is exactly the score of the target V divided by the sum of the score of its neighbors. That's exactly the choice, right? Imagine that you're doing a random walk. I choose according to the MNL process, and this is what I'll get. So let me skip this example. It's very clear what it means. What it really captures is the fact that the transition probabilities are context independent. That exactly brings back to the question Joel asked. If I'm given with a bunch of like 10 bad restaurants, the choice probabilities would be very different than given 10 bad plus 1 good restaurant, right? Because it's naturally the denominator captures that. That's what this one is good about. And the motivation for studying this model is that so we were looking at how people browse on YouTube. So in YouTube, you go to a video, you finish watching, at the end it gives you a bunch of recommendations, right? So you can think of that as like a random walk. You're doing a random walk on this the graph of videos, and what we know is that I know how many times each video is observed. I know the view counts, how many times people watched it, but I want to construct the Markov chain where how people actually make the choices. That we don't know. So in other words, the problem is you're given you're given a steady state. I want to find out the Markov chain for which this is a steady state. In other words, I want to find those scores for every nodes such that I can that the scores induce this Markov chain with the given steady state. Okay, that's the problem that we looked at, and it turns out that I actually can solve this problem exactly in polynomial time. It's a very clean algorithm. So given any graph under some very mild conditions and given any stationary distribution, you can first of all, you can show there is a unique set of scores that define the Markov chain for which pi is a given target, and you can find this scores up to an arbitrary precision with an algorithm. So I'll skip the algorithm. It's a simple like learning algorithm, and showing that actually it works is the harder part. Yeah. Okay. So I want to conclude by saying that I hope I motivated that there's a lot of interesting problems in relative discrete choice, very interesting algorithmic problems, and I believe that there are this is areas not as understudied by especially by computer scientists, and I think there's scope for many open questions. Some of them I'll indicate. This is my favorite one. The algorithm I showed you for 2 MNLs works only for uniform 2 MNLs. We don't even know how to extend that to non-uniform 2 MNLs. Talking about now, I don't know the mixing weight. So I don't know the mixing weight, I don't know the 2 MNLs, I know that 3 slates are not enough, we need 4 slates at least. But to prove that these are identifiable, it's still an open question.
This is highly relevant, right? Because the proportion of people going to vegan restaurants is not a half.
Yeah, exactly, yeah, exactly, it's highly relevant, yeah, we don't even know the proportion. So this is a simplest question that we don't know how to answer. And I think that there is opportunity for many things. So with that I'll stop and thank you.
Thank you. Some more questions? Yes.
It seems that this problem is much related to the random linear assignment problem.
Yeah.
The matching
Max.
there's a lot of work on this on the random assignment problem.
And I see.
So this also has consequences on this
I see.
projection.
I see.
What is the, for example, cell distributions, what is the value of mass and so on.
I see. Okay. I'm not aware of that work, yeah. Thanks, I'll look up.
Yeah, in the back.
I'll answer him, yeah. Okay.
Okay, so the things which you have assumed is kind of stationary. So if it is dynamic, then will it be with some changes can it be solved? I mean, if you talk about restaurant or tourist places or anything on YouTube channels, so what happens sometimes it starts declining due to some reason. So is there some way to deal with such problem? I mean, we can start with 0 or we should allow it decline.
It's a very good question. So the question was whether you can assume if the scores, the last problem I posed, if the scores, if the stationary is changing, can you do anything? But it's a very good question, so I don't know the answer. So, yeah, question.
Yeah.
My question is about robustness. Assume I'm discrete or something, and there is a small probability of mistake, and actually I'm not I do not have answer it. And assume I am from group A, but
Right.
my preferences
Okay.
are slightly different. Can this influence the result like really hard, or will it not change?
So there are two parts to that. One is that if there are the clicks or if the answers are noisy, what do? That is okay because you assume apply law of large numbers, right? If you have enough samples, then assume that things are done, exactly or close to exactly. Second part is tricky. If I kind of end up in the wrong group, then I pollute both sides, right? So that I don't know how robust the results are. It's a good question. So I assume that the results are not that robust because very soon you'll get into the lower bounds. So yeah, I don't know. It's a good question to study.
Yeah. Okay, one last question, Bruce.
So what about, you assume rationality, right? You don't assume rationality anymore. Have you thought about any models that would include that?
So not me, but I think economists have thought about models to include that. Yeah, it's a good direction.
Thank the speaker again.